Alright, so for section 1.2, I've got three different suggested examples for y'all. Example 2 on slide 36, example 3b on slide 42, and example 7 on slide 65. Again, these are problems that I'm not going to go over in this presentation, but they are problems that I believe you should check out on your own because they're good problems to get you used to the material, to really check if you understand what's going on. Having said that, let's see what I do have in store for y'all. To start off with, let's imagine we wanted to graph an equation, because I know that's everybody's favorite pastime, right? So we want to sketch the graph of this equation, y is equal to 7 minus 3x. How might we do this? What's the first step we might want to take? Well, one obvious first step, obvious, most dangerous words in math. One obvious first step we might want to take is to get a table of values, right? Plug in an x value, get out that y value. And just make a table of these. A good one to start off with might be 0, since it's easy to calculate things when x is 0, right? So to start off with, let's plug in 0. We're going to get out 7. And now let's do this a whole bunch. And let's get out a couple different points. Now notice, what we've done is we've said there's an x location associated with a y location, right? That's all this table's doing. And when we do that, we've just created a table of ordered pairs, right? Like these are just points. Each one of these columns just represents a new point. This is our x position, this is our y position. That's it. So knowing that and using that, we can now graph our equation. You say, all right, I'll take all these points and I'll just throw them on a graph. And then I'll connect them with the appropriate line or curve. That's all there is to it, right? Now, having said that, the next obvious question is, yeah, but how can I make this easier for myself? Well, one thing you can do is find intercepts. So what are intercepts? Well, intercepts are just parts of your graph, of your equation, that goes through one of the axes. So if you have an x-intercept, your graph goes through the x-axis. So that must mean that y is equal to 0, right? Because that x-axis, that's what it represents. That's the axis, that's the line. Y is equal to 0, x is equal to something. X-intercept. Similarly, y-intercept goes through the y-axis. And it's got to be your x value that's equal to 0. So knowing this, you can say, all right, I've got my equation. Let's set x equal to 0. That's going to give us our y-intercept. Now, once we get all of those, let's set y equal to 0. That's going to give us our x-intercept. And just as an example of all the different variations of intercepts we might get, right? Like we could get a whole bunch of different combinations of intercepts. We might have no intercepts. We might have 3 different intercepts, 2 along one axis, 1 on the other. We might have another 3. We might just have 1. We could get all different arrangement of intercepts. Having said that, let's check out this example 3a here. So we want to find all of the intercepts, x and y, for this equation y is equal to x cubed minus 4x. To do that, the first thing we'll want to do is to factor our equation, to make it nice and easy for us to work with. So we factor out our equation, and we get that y is equal to x times the quantity x plus 4 times the quantity x minus 2. Okay. Knowing this, we then set y equal to 0. We say, all right, well, if y is equal to 0, then that's got to mean either x is equal to 0, x plus 2 is equal to 0, or x minus 2 is equal to 0. And the reason why is because these are three different quantities being multiplied together to get 0. Well, the only way you can multiply any combination of things together and get 0 is if one of them is 0, right? A times B can only come out to be 0 if either A is 0 or B is 0. And because of that, we know that either x has to be 0, x plus 2 has to be 0, or x minus 2 has to be 0. So we can say, all right, well, when are these things going to be 0? Well, x is going to be 0 when x is 0. That gives us 1 over here. 0, 0, right? Because that's what we're solving for. Y is equal to 0. Okay. Well, the next case is if x is equal to negative 2, right? Because if x is equal to negative 2, well, negative 2 plus 2 comes out to be 2. Or it comes out to be 0, sorry. So, we know that this has to be negative 2, this x value has to be negative 2, for this whole thing, this little piece, to be 0. Okay. So that gives us a new order pair, negative 2, 0. And then finally, this one, this little bit here, is going to tell us when x is equal to 2, y is equal to 0. So, a new pair, 2, 0. And from this, we get that we have three different x-intercepts. Now notice, the very first case, we set x equal to 0. So that's one of our y-intercepts too then. In this case, there's our only y-intercept. We only have the one. In plotting all of this, we get these three different points. And this is what our graph in the end will look like. So notice, if you knew kind of what the shape of this graph was going to be, just having these 3 points got you a long ways, right? If you knew that x cubed minus 4x was going to kind of be this sort of an N shape, now having these 3 points, you're halfway home. You just need to know where this peaks out at and where this peaks out at. Troughs out at, I guess. I guess this would be a troughs out, not a peaks out, but you know what I mean. Having said all this, let's move on to the circle. The circle is pretty straightforward, actually. So the circle is going to have a center that we call the points HK. We're just going to go ahead and name them for now. And the radius of the circle, we're going to call R. For now, this is all we need to know, right? Just the basic anatomy of it. It's a center point that we call HK, enclosed by a circle of radius R. Okay. Cool. But using this information, having just these two things, tells you a whole bunch about what the equation of that circle is going to look like. The standard form of the equation of a circle only requires you to know HK and R. By knowing just those two things, you can plug those values in and get the equation of that circle. The equation is going to be x minus h, that quantity squared, plus y minus k, that quantity squared, is equal to your radius squared. That's it. So, with that, excuse me, let's imagine that we've got this circle. The circle is centered at negative 1, 2, so that's our HK, and on its boundary, there's this point 3, 4. pretend like this is a well-drawn circle. It's not. So our center is somewhere over here. And there is a point somewhere over here. Like I said, this is not drawn to scale. It is not a good circle at all. So please squint your eyes, tilt your head, and laugh at me if you have to. So the center point, HK, is equal to -1, 2, and this far out reaching point is going to be the point 3, 4. So it doesn't quite tell us all the information we need, does it? It doesn't tell us what the radius is. But somehow we're going to get that information from this problem, from this setup. The way we're going to do it is we're going to say, well, the radius is going to be the distance from the center to this point here. So by applying the distance formula, we can get the radius of this circle with just these 2 points. So, center to that outer point, we're going to find the radius. When we do, we're going to find that the radius is equal to the square root of 20. And plugging everything into our equation, this -1 for h and this 2 for k, we're going to get that our final equation comes out to be x plus 1, the quantity squared, plus y minus 2, the quantity squared, is equal to 20. Now, just as a kind of a cosmetic sort of a thing, in homework, on exams, whenever I need you to show your work, I could get beyond y'all not showing this particular stuff right here in the middle. And the reason why is because we all understand if you subtract a negative, you're just adding. And if you square a square root, just taking the absolute value of what's interior to your radical. So I can forgive y'all if you skip that step. Like, that's understandable. Having said that, there's another form of the equation of a circle. There's this alphabet soup looking form. It's called the general form. ax squared plus ay squared plus dx plus ey plus f is equal to 0, where a is not equal to 0. Oh, okay. Let's say that backwards. That'll be fun. New sobriety test. Alright. So knowing this, what might we ask? Well, we might say, is this a circle? 1. 2. If it's a circle, put it into standard form. So, if we want to sketch this, if we want to graph it, let's put it in standard form first. We know how to use that. That's easy. How are we going to put this into standard form, though? Well, we're going to have to do what's called completing the square. And even then, we still, once we get to the end here, don't necessarily know that we're going to end up with a circle. I mean, this problem tells us we will, but I'll explain what I mean in a second. Alright, so to complete the square, once we've completed the square, I should say, we'll get it back into a form like this that we can easily turn into our standard form. Having said that, I want you all to notice something. Notice that we've got our x minus h, that quantity squared, plus our y minus k, that quantity squared, is equal to r squared, right? So let's think about this. If this were negative, it can't be a circle, right? Because if it were negative, if what we got after completing the square was negative, then that means we have to have an imaginary radius, right? Because this is r squared. And if we have to have an imaginary radius, then what we're looking at cannot be the solution to a circle. And that's what I was trying to say before. So, if given an equation in that general form, we don't necessarily know right away that it's a circle. It's not until we complete the square and see that the radius is not imaginary that we can know for sure our general equation was of a circle. If anybody has questions about this, please feel free to shoot me an email, because I know that can come off a little confusing. Having said that, looking at the rest of the solution to this problem, we got it into standard form, right? From there, we were able to graph it right away. It's pretty quick and simple, right? Because we know that HK, that's the center. We know r squared, it's radius squared. Since r squared was 1, radius has to be 1. We're done. It's that easy. Having said that, I know that it's not actually necessarily easy. When I say it's that easy, what I mean is don't overthink it. That's what I'm trying to say. It is easy for all of us to get into those situations where we're like, the problem's beating me, I'm getting aggravated, I'm getting angry, I hate it, I want to walk away from it. Stop. Get up, go do something else for a little while. Don't let the problem beat you, one. Because once it's beating you, you're not coming back to it, right? Like, once it's beating you, you can't enjoy it anymore. And math is actually, if you let it, an exceptionally fun subject. So when I say it's that easy, understand that I don't mean that it's actually easy. I know it's not. What I'm saying is it's an algorithmic approach. It's something that with practice and with some time, you're like, oh, I can solve these all day, all night. Cool. Let's move on though. Points of intersection. So, points of intersections are going to be really important to business in particular. When talking about things like supply side economics, or trying to figure out what the right price of a commodity good is, if you want to break even at a certain point, et cetera, et cetera, et cetera. All sorts of reasons why points of intersection are going to be important to us. And all point of intersection is, is when we said two equations equal to each other. And we say, all right, if these two equations have a point in common, what's the solution to setting them equal? What is that x value we're going to get out? And what's the associated y value? That's all it is. So, in this example here, we've got the equation x squared minus 3. We've got the equation x minus 1. We want to find the point in common, or points. So we set x minus 3 equal to x minus 1. From there, we're just going to solve for x. And when we solve for x, we're going to take that solution, or solutions, and plug them back into either of our equations. So let's look at an example. As an example, we've got this company that's trying to figure out when it's going to break even. This company is producing a thing at 65 cents per unit. But like every company, they've got to have some initial investment to be able to produce it, right? Like you got to build your factory first. So their initial investment is $10,000. Having said that, this company, when they sell their thing, they have it marked up as $1.20 for every unit they sell. So, looking at this, looking at this, our first equation, let me erase this really quick here. Our first equation is going to represent the cost. The cost is going to be 0.65 x plus 10,000. The revenue that they're going to make is going to be $1.20 for every unit. So the revenue, that equation, is going to be just 1.20 times x. Now for this problem, we're going to set them equal to each other. We're going to try to find this point right here. And looking at this graph, we can actually see why this makes sense, right? Because everything below that point is going to be loss. That's when you're losing money, right? And everything above that point, that's profit. You're making money. You're in the dough. You're raking in the cheddar. You're making everybody happy. All right. So how are we going to find this point? Well, like I said, we're going to set our two equations equal to each other. And when we set them equal to each other, it's going to look something like this, right? We've got our cost equation, we've got a revenue equation. We set them equal. We get 1.2x is equal to 0.65x plus 10,000. We try to move this 6.5x to the other side. When we do, we find that it's now going to give us that 0.55x is equal to 10,000. So we can divide both sides by that decimal, right, to solve for x. And when we do that, we're going to get approximately 18,182, approximately. Having said that, I'm skipping over a little bit in the notes, mathematical models, and that's because I think y'all can read that and understand it for yourselves. But I did want to point out a couple of different types of models that show up regularly. We've got the linear model, we've got the quadratic model, the cubic model, the square root model, the absolute value model, and the rational model. And the reason why I want to point these out to you is because recognizing these right away will get you a long way in this class insofar as graphs are concerned, right? Like, if I presented you with a graph and you knew all these different types of models, you could generally figure out what the equation might be just by knowing what these look like. Having said that, that is all I've got for y'all. So, have a good one.